Hello, and welcome to today's webcast. My name is Dennis Semeka, Associate Editor at Vision Systems Design. The speaker for today's webcast, How to Deploy AI and Deep Learning for Quality Inspection, is Stephen Welch, VP of Data Science at Mariner. A few housekeeping items before we begin. If you have questions or issues during the webcast, please click in the Ask a Question area at the bottom of the console. We'll try to answer as many of your questions today as possible. If you experience audio issues during the webcast, please try refreshing the page. If this doesn't solve the problem, or if you have any other issues during the webcast, please click in the Ask a Question area of the console, tell us about the issue, and a member of the webcast support team will work with you to correct your issue. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from our homepage. The slides will also be available for download today. These can be accessed via the Event Resources tab under the Ask a Question area. Before we begin, I'd like to thank today's sponsor, Mariner. And now it gives me great pleasure to introduce Stephen Welch.
Great. Well, thank you so much, Dennis, and thank you to everyone for your time today. We really appreciate it, and we hope this is a good use of your time. We're going to talk about some pretty interesting areas. My name is Stephen Welch. I'm VP of Data Science at Mariner, and I'm also an adjunct professor at the University of North Carolina teaching computer vision. So I'm going to go ahead and hop right in. What we'll kind of do today, I want to talk about some of the challenges and opportunities in deploying computer vision for quality inspection. But I find that it's helpful to start with a nice tangible example, right? So we'll walk through one customer example briefly, and then we'll kind of zoom out and think about, what are some of the challenges, what are some of the technologies, and what are some of the opportunities for deploying these systems. So just to make it really specific, here are 4 images from one of our customers. These are real images of fabric. I'll show you the machine this comes from in a second, but just for a minute so we can kind of get our head into the space of where these computer vision algorithms live. Just take a second and see which of these images you think shows a defect. We have a survey, so you can actually participate in that. We can see what you have to say. So let me send this survey out to you here. You should be able to see this survey shortly. And while you're thinking about that, while you're thinking about, which of these images of fabric show defects, let me share a little bit about the use case and the hardware behind these images. So these images come from an existing vision system. And like many vision systems today, this one has excellent hardware and imaging capabilities. So here's a picture of the image system on the upper left-hand corner. It's a huge machine. It's about 14 feet wide, 12 feet tall. It has 8 high-speed cameras in it. The rolls of fabric are about 10 feet wide. They fly through this machine at about 85 yards a minute. And wherever the machine detects the presence of a potential defect, it snaps a picture. And then does some decisioning on those images. And the output of that vision system is what's called a defect map. And you're looking at a defect map on the bottom of the screen there. So the the vertical axis is the width of the roll of fabric. That's in inches. So it's about a 10-foot wide roll of fabric. And the x-axis is the length of the roll. So it's about a half a mile of fabric. So a really big roll of fabric. Every dot on that roll corresponds to a location where the current system believes there to be a defect. Now, in practice, as I mentioned, this system has excellent visioning capabilities, but it struggles with an issue that many systems for decades have struggled with, and that's the issue of false positives. It can be relatively simple to get these systems to detect defects, but the challenge is teasing apart true defects from things that look kind of like defects but aren't. And we'll get into that in more detail. But in practice, what was happening for this customer, at least, is their system, it had excellent images, but in practice, around 40% of those dots on the bottom are not actually defects for this customer use case. What that meant, that high false positive rate, it meant that they had to change big parts of their production and use manual inspection. So it really prevented automation, and it really slowed things down. Ultimately, a map just like that one is used later in production to actually cut out defective sections of fabric before it's shipped to a customer. So these maps really, really matter, and the quality of the maps is directly connected to the quality of the product that you ship. So that's a little bit of background on the problem. And let's talk just a little bit about traditional machine vision, and then we'll hop into the answers to the question that I posed. So I think a good question to ask, is if that's kind of existing technology, and we know that in some cases it can struggle with false positives, why is that happening, right? What's happening under the hood of the system? How does it work that causes some of these problems? So if we look at traditional machine vision, especially in quality inspection, these systems have been around for quite a long time now, so really since the 1980s. And traditionally, these systems work using a two-step process. So there's some kind of image capture component on the left, a camera, a line scanner, whatever. That's connected to some kind of compute component running some kind of software. And inside of that software is really the brains of the operation. That's the computer vision algorithm actually doing the processing. And traditionally, this computer vision algorithm has been broken into two sections. So the first section is called feature extraction. And the big idea there is that we're going to apply some mathematical operations. We're going to do some math to pull out what are hopefully good measures or metrics that can help us make a decision. So for example, in that image that you see on the screen, kind of the glowing purple and yellow image, that shows the contrast of various windows of the image. So what we're doing is we're taking a sliding window detector, sliding it across the image, and wherever there's a high contrast, that is the difference between the darkest and the lightest pixel, that results in a high contrast value, and you see the image kind of glowing, right? So high contrast regions like that could be indicative of defects or a bad product. Not always, but it could be, right? You can imagine that contrast alone is generally not enough to make a decision, right? So features like contrast are combined with other features. Another common one would be defect size, right? Can I measure the size of that potential defect and use that to make a decision? So that's feature extraction. That's step one in traditional computer vision pipelines. Step two is always some kind of decisioning step. This can be accomplished with machine learning, but in a lot of cases, this is actually accomplished using kind of a recipe. So an algorithm designer will set up a recipe for a certain kind of product that actually manually sets thresholds, right? So if contrast is bigger than 100 and defect size is bigger than 10 pixels, it must be defective, right? That kind of thing. So that traditionally is how computer vision systems have worked, really for a long time. So with that in mind, let's hop back to our question here. So which of these four images of fabric do you think are defective? And let me hop into my survey here. Let's see if we can see some results. Okay, cool. So I'm going to send results back to you so you can see them as well. And let's see here. Let me go back to my slide here. It looks like, and I'll walk through them one at a time. So the first one here, this is a good image. Most of you got that right. Great job. Number 4, way on the right side, that is a defect. That's a big hole in the fabric. The tricky ones are the center two. So let me go ahead and go to the answers here. So number 2 actually is defective. So that is a stain on the fabric. A piece of a drop of oil has landed on the fabric, causing a stain. The third example is actually good. This is the tricky one, right? So to a trained expert, so our customers, quality engineers, they can tell these apart no problem. They know that third example is actually what's called flock. So that's a piece of debris or lint on the fabric that can just be rushed away in the next process. And it's not a true defect, right? So images like this are a big cause of false positives in these vision systems. And if we kind of think back to how traditional computer vision works, like we just talked about, right, the feature extraction and the decisioning, telling apart 2 and 3 using traditional computer vision techniques is really hard, right? So they have very similar contrasts. The darkest versus the lightest pixels is quite similar. And they have similar sizes, right? And there are other features you could certainly extract, like you could try to extract something about the hardness of the edge, but it'd be very difficult. This would be a very difficult problem to solve 10 years ago. So flash forward to today, and this is what we're doing at Mariner with our product Spyglass, and this is broadly where we think the industry is going for many quality inspection problems. So we are replacing that 2-step feature extraction followed by decisioning with a single deep learning model. There's a big good reason to do this. The big reason is performance, and we'll get into some performance numbers soon. But I also want to make you aware in this presentation that there are some real trade-offs, and that's what we'll get into with some of the deployment challenges. And those trade-offs really come around because of the central shift in focus by changing to a deep learning-based approach. So the system on the left, traditional machine vision, It's very what's called analytical, right? So when we say analytical, I mean an engineer sits down and kind of designs this from engineering principles, right? So a computer vision expert comes in, figures out what features make sense, designs a recipe for decisioning, and that's shipped to a customer once and deployed. On the right, when you use deep learning, all of a sudden you're actually training the model from data. So that's kind of your source of truth now. So you're shifting data to the center of your process, and that really matters for deployment and maintenance and all these things. And we'll get into that shortly, but just be aware of that, I'd say, as we get into it. Now, let me answer probably the more important question, which is why, right? Why replace this technique that works in many cases? Why switch to deep learning? So here really is, I think, this is how I would argue that we should switch to deep learning in many cases. Not all cases, but in some cases, this is a huge shift that we should make. So let me walk you through this. So this is performance on an open source data set called ImageNet. ImageNet is, and definitely was back in 2012, the most difficult computer vision challenge out there. So it represents around 1 million images. So the ImageNet data set has roughly 1 million images. Each image has been labeled by a human, and the labels correspond to things like cat, dog, chicken, there's all kinds of different classes. There's a total of 1,000 classes in the ImageNet competition, and your job as an entrant to this competition is to classify the image correctly, right? Can you correctly classify what an image contains? So back in 2011, the very best algorithms in the world had an error rate of around 26%. That's that 2011 column there. And that's with 5 guesses, right? So if you gave the algorithm 5 guesses, it only had an accuracy of 74% or something. So this is not ready for deployment. This is not going to work in a manufacturing environment. In 2012, something exciting happened. So these researchers at the University of Toronto, led by a researcher named Jeff Hinton, they published a paper called AlexNet. And in that paper, they use a deep learning model, this unified deep learning model, which we'll get into a little bit more later. But by doing that, by switching from, and more broadly, back in 2011, the dominant paradigm was that 2-step process, right? Human designed features plus decisioning. In 2012, we switched to this unified architecture, this deep learning model, and performance improves by 40% in 2012. But that's huge. This is a really difficult data set. The really exciting thing, though, I think, is in the subsequent years, using, again, deep learning, but with various modifications and improvements, researchers were able to get to superhuman performance in 2015. So with a model called ResNet out of Microsoft Research, researchers were able to, for the first time, outperform humans on this data set. So this ResNet deep learning architecture, that's what we deploy in almost all of our deployments. And we'll get into some results very shortly as, how does ResNet do on these kinds of data sets. So that's why we are advocates of deep learning and why we think it's having a big impact already and will continue to have an even bigger impact. But let's get into some of the details. I think with this audience, you guys probably want a certain level of detail, and I'm going to try to provide some really tangible results and examples that will hopefully expand your understanding of some of these technologies. So here are some results. So this is from the fabric example that I showed you. So these are our initial results for this customer. We've anonymized it a bit because of our NDA. So what they were interested in, the numbers are correct, but we've changed the defect names. So many customers will start with just trying to tell apart good products from bad products, which is fine. If you did that, you'd have 2 classes, right? Good and bad. For this customer, and for almost all of our customers really, they quickly realized that there's a lot of value in classifying more than just good, bad. So for this customer, they started with 3 non-defect classes. So those were things like that flock that I showed you on the question. And they started with 6 different defect classes. Detecting different kinds of defects can be really valuable. We'll talk about it a little bit more later, but you can tie that back to earlier parts of production. If you have a large number of stains, that means that a certain kind of machine is probably causing that, so you can identify and fix production issues faster. So that's where this customer started with 6 different defect classes and 3 non-defect classes. And this plot here, which I haven't explained what the plot is yet, this is a confusion matrix. I'm sure many of you are aware of it, but I'll talk through it briefly. And this shows us how our ResNet deep learning model did compared to the labels from humans. So I haven't gotten into this in too much detail yet, but at Mariner, we largely use a technique called supervised learning, which means that to start these processes, we start with a labeled data set from our customer. And labeling just means, like I described earlier, telling us what is in an image, right? So they started with around 500 images, and for each image, they told us, this is defect type 1 or defect type 2, or 3 or non-defect, or they gave us the class. So the rows of this table, those represent the labels from the customer. So if you look at that 108 in the upper left-hand corner, that represents 108 images where the customer said, hey, this image contains non-defect type 2. And if you look at the column, it's in column non-defect type 2 for predicted, which means our model agreed in those 108 cases. So in those 108 cases, we got right because the row and the column name match. So then a perfect model would have only entries on the diagonal, right? And everything off diagonal is wrong. There's a few things off diagonal. If you look at that 4 on the fourth column, those are 4 examples, fourth row, excuse me, that 4 on the 4th row. Those are 4 examples where our human labeler said this is defect type 1, and our machine said defect type 4. So different kinds of confusions can have different costs to your business, and it's worth paying attention to how your model is getting confused. So let's zoom out a little bit. So these are the ResNet model results, and we'll share some more ResNet model results shortly. But this achieves an accuracy of around 98%, 97.7, which maybe sounds good. It's important early on to tie this back to real production. So accuracy is okay, but usually that's not going to translate directly into dollars and cents or whatever you're trying to optimize for. In this case, for this customer, it made sense to measure 2 things. So we measured, first of all, the false rejects reduction. So they had, as I mentioned earlier on, a big problem with false positives with those false rejects. They had a false reject rate of 40% or something. So using this approach, we were able to reduce that 40% rate to like 1.3 or something. So that is a 30x reduction on average. So this is not 30% better, it's 30 times better, right? So this is where people get excited about deep learning. And there's certainly areas where people are overhyping deep learning, and it's kind of a hot topic right now. But when you find the right problem, it can deliver dramatically better performance than previous approaches. The other thing that we compare to is human inspection. So when we compare our performance rate, our capture and our false positive rate versus humans, we're around 2 to 5 times better on average. And you may be asking yourself, hey, Stephen, how is it that this model is beating human performance when it was trained off human labels? And the answer there is that the labels kind of come from your experts on a good day with enough time to think about them, right? So your experts can sit down and really make a well-curated data set to train the model from. We're comparing our model to inline human graders. That's a really hard job, right? You're watching fabric fly by at a high rate. You work in 8-hour shifts. It's very hard to achieve the quality you need with manual visual inspection like that, especially for products that are on rolls, right? So that's how we're able to get superhuman performance in this application. So I'll just share one last slide on this application, and then we'll kind of zoom out and think about the bigger picture. So the top plot shows the defect map before, and all of those dots that have been removed are the false positives. So the bottom plot is the output of our system. And we're correctly able to, with 98% accuracy, remove all those false rejects from the roll. And this really has a big impact on their overall process optimization. So that's a specific use case. Hopefully that made some sense. And now I kind of want to zoom out here, and I'm going to do one more survey. So I'll go ahead and launch the survey first. So let me go over to the survey thing. Okay, so I just sent out a survey. And this is going to connect to actually a survey that was actually in this magazine. So this is an image from a Vision System Design article back in December. And this is a really great article. It's got some great numbers in there summarizing kind of the state of the art or what's going on in various verticals. And what we're looking at here is we're looking at the penetration of deep learning into various verticals. While you take a second to look at the survey, I'm going to take a quick sip of water. Okay, great. So let me hop to the survey here. Let's see. Okay, so it was sent out. Oh yeah, great. Okay, and I'm going to send the results back to the audience. So I think your results, so if you look at the slide, right, these are the results from the survey back in December that Vision System Design conducted. In your survey, let's see, I think it lines up pretty well. So around half of the audience is not using today but may use in the future. Around 16% do not use today. About 16%, oh, it just updated, that's cool. Wow. And then about 18% use it often today. So that's great. So about a fifth of you out there are using it often. but the majority are not using today, but may use it in the future. And I'm going to send this, I don't know if I have to send this again or not, but the results updated a little bit, so I'll make sure you have the most recent results. So that's pretty cool. So when we look out there at the landscape, deep learning is definitely still far in the minority, right? So it's not, by no stretch of the imagination, is it the dominant computer vision technique for quality inspection. Now, there are problems, certainly, where deep learning is not the right solution, where traditional approaches are just better for a number of reasons, and you should not use deep learning. We do believe, though, as part of talking to a lot of customers and learning a lot about the problems out there, that deep learning still has a lot of room to grow. So I think the question that I want to explore now is, if it's so great, if you can get the results I just showed you, why has it not been adopted more, right? What is slowing its adoption down? That's the question I'd like to use to frame the rest of our conversation here. And when we look at the space, and this will really lead us into the challenges and the deployment and what really goes into these systems. When we look at the space, I think there's a few myths out there and there's a few challenges. And we'll kind of walk through those one by one. And I think this will give you a sense for how we see deep learning in 2020 in quality inspection. So let's go through the myths first. So the first one is that deep learning models need to be trained on very large data sets. So let's hop right into that. And I think the best way for me to address this is to actually show you a real example. So as part of preparing for this webinar, I trained some models, and we'll show you some real results. We're going to use this data set from a company called MVTech. They make a computer vision product called Halcon. And they are doing an excellent job at publishing open source things, which I think that's fantastic. There's not a lot of open source data in manufacturing and in quality. I wish there was. It's growing slowly, but MVTech has done a great job and released this data set you're seeing on the screen here. And over about 15 different product classes, they give us between 300 and 500 labeled images, which is fantastic. So what I want to show you is I'll pick a few categories. We'll train a deep learning model, and we'll see how it does with smaller data sets. So I'm going to start with this leather category. So first of all, let me talk you through the labels briefly. So the columns there represent each label in the data set, and they break apart their data into, they have 5 different defect classes and 1 good class. There's a bunch more examples of good than defects. That's pretty typical. And also this data set is targeted at unsupervised or 1-class learning. We won't talk about unsupervised too much today. If you have questions, though, please ask at the end or reach out to us. But so that's the leather data set. And before we hop in, though, we need to decide what kind of model we're going to train. The simplest model out there, and kind of the model I've been talking about, is what's called a classification model. And the idea in classification is that the input is just an image, and the output is a label, right? So I'm going to give you an image of leather that has a fold in it, and the model is going to say fold, right? So it just predicts, hey, somewhere in this image there is a fold. That's kind of level 1. And we encourage customers to look at classification first. So detection, there's lots of fancier methods out there, but labeling for classification is really easy, and it's a good way to get projects off the ground. So we recommend that as a good starting point generally. If you need something more sophisticated, then detection can be a nice step up. So if you need to know where a defect is, in addition to whether or not it's present, you can train what's called a detection model. And that will give you the class. It will say, okay, I found a cut, but it will also give you a bounding box. So it'll say, okay, the cut is exactly here. And in certain applications, you need that, right? So it's a good tool to have at your disposal. Finally, there's more methods than this, but these are kind of the 3 most common, I would say. There's a method called segmentation, and this goes a step further. So instead of just saying, okay, this whole image contains a fold, I'm going to make a prediction for every pixel in the entire image, right? So that's a lot of predictions, right? But you can see, like, if you look at the glue image on the bottom left, those blue pixels in the glue image, those are the pixels where the glue spot is, right? So some applications demand that level of precision, and if that's what you need, then segmentation is a great option. Today, we're just going to explore classification, but really the results I present here will generalize pretty well to detection and segmentation. So let's get into some real results here. So again, I just want to give you a sense for the kind of data set you need to train these models. So here again is the MVTech leather data set. And we're going to train our model to detect those 6 different classes, good, glue, cut, poke, fold, and color. We'll train what's called a ResNet 34 deep learning model. It's called 34 because it has 34 layers. It's a pretty common architecture, kind of a middle of the road. We'll do an 80-20 split, so we'll randomly say we'll reserve 20% of our data for testing, and we'll train on 80%. And we'll show you two techniques. So the first technique we'll show you is training ResNet34 like from scratch. So when you train these models initially, you actually initialize them with random weights, and they learn these weight values that do the image classification. That's how that AlexNet model was trained that I showed you back a few slides ago when we trained it on, they trained it on, the ImageNet data set with 1 million images. We'll do that, we'll train from scratch, but then we're also going to use another technique to show you called transfer learning. And what we're going to do there is we're going to take a ResNet34 model that was trained on ImageNet, right, to some good performance level, and then we're going to do what's called fine tuning. So we take that checkpoint, that trained model, and then we train it further, but instead of training it on ImageNet, we train it on this leather data set, right? So that's called transfer learning or fine tuning, and we'll show you that result as well on the next page. So that's the experiment we'll run here. So here are the results. This is the result of training a ResNet34 model. So on the left, you can see training from scratch, and training from scratch, that's really the kind of application or use where you do need more data. But if you do the transfer learning approach on the right, where we train from that checkpoint, from that saved model configuration, we actually get 100% accuracy on this data set, and it takes 10 minutes. So that's incredible to me. I mean, this just was not possible 10 years ago. This was completely out of the realm of possibility. So hopefully that shows a little bit of what you can do with small data sets. You don't need huge data sets, especially if you don't have a ton of classes, right? So don't let data set size discourage you from pursuing deep learning. Let me show you another example just to prove it's not a fluke here. So here's carpet. This is another MVTech example. Notice the number of defects we have, right? So we have 17 examples of metal contamination, 17 examples of cuts, 19 threads. So not very many, right? And some of those images are tough. So if you look at the metal contamination, that's a piece of metal that's on the carpet. And the authors of this data set, they have decided to pick a metal color that is very close to the carpet color, right? So using traditional computer vision, it would be difficult. I'm sure you could do it, but it'd be hard to tell apart the metal from the background. And I think it'd be difficult to get that into production using traditional computer vision. So here are the results on that data set. So we train in about 15 minutes, and we get one wrong. The one we get wrong is we mistake a hole for a thread, and that's actually the upper left image in that pane. So we get one wrong. And again, a very small data set, right? We're talking about tens of examples of defects here. Okay, let me show you one more. I intentionally picked a class that would be difficult now. So this is the screw class, and I want to show you that deep learning is very powerful, but it can't solve every problem in the world, and it can't solve every problem in the world without much data. So here's a harder example. Let me walk you through this briefly. So these are screws. And the defects we're looking for here are really subtle. So if you look at that manipulated front, right, just the tip of the screw is kind of bent inward, right? So that's a very subtle defect. When we do come across examples like this from customers, we usually encourage them to collect bigger data sets. Normally we want to start with at least 50 examples of each defect. And this is a little bit, well, it's actually significantly less than that. So here's how we do. We get to around 74% accuracy. That's okay. Like I said, if this was a customer deployment, we would first ask for more data. And we would also consider training a detection model, because a detection model could actually focus in on the specific areas that you're looking for. But out of the box, ResNet34 classification does not do great. So hopefully that gives you a little context for what's possible with small data sets. And that really is a myth. I hear it all the time. You do not need huge data sets to train these things. The next myth that I want to hop into here is that deep learning models take a long time to train. This has also been around for a long time, this myth, and it used to be true. The AlexNet model back in 2012 took like 2 weeks to train, something crazy. But that's changed dramatically. So let me show you an example from production. So I told you that some of those earlier models, took on the order of 10 minutes to train. But those, you could argue against me, hey, that's 300 examples. How does this stuff actually scale into production? So here's some real numbers from a real customer. So this is a customer we've worked with them for a while and have made a really great large labeled data set. So they have around 35,000 labeled examples, which lets us do all kinds of cool experiments. I love having access to data sets like this. And what I've done here for this webinar, just to show you how this stuff scales, is I ran some experiments. And on the x-axis, I'm plotting, how much of the data do we use to train? Because if you have 35,000 examples, you could easily train on 1,000, 5,000, 10,000, that kind of thing. I will note that this is a hard problem. So this manufacturer has very subtle differences between good and bad product, and they have around 20 different classes that they're looking for. So this is what I would really call a production grade application. And on the plot on the left there, you can see how long it takes to train our model as a function of our data set size. So we're conducting 3 trials for each data set size. Those are the 3 dots you see at each vertical location. And the solid line is the average. So that's the average training time. So you can see that for around 5,000 examples, we're talking 20 to 30 minutes. And then once you get to 30,000 examples, you're at about an hour. So this does scale linearly. There's no exponential growth. And it's still very manageable, right? I can train a production grade 30,000 example model in an hour, right? So that's not prohibitively slow by any means. In case you're interested, you can see also how the accuracy increases with the data set size, which is, I think, also very interesting. I'll keep moving for now, but I wanted to share that as well so you could get a sense for how the data set size impacts performance. One great thing about deep learning is that performance does generally scale quite well with your data set size. Okay, the last myth that we run into is that you need a data scientist or machine learning expert on staff to use deep learning. Back in maybe 2012, maybe all the way to 2015, 2016, that was definitely true, but it's certainly not true anymore. All the results that we've shown you today are from our product, Spyglass Visual Inspection, and we're built on what we consider to be the best of the open source. So we leverage PyTorch, a library called FastAI. So really the tools are out there, and there's products and solutions like Spyglass Visual Inspection from us, and there's other products out there as well that really abstract this complexity away. And really what becomes important in our experience is not so much the deep learning tooling as the subject matter expertise, right? So once you get the modeling set up and the infrastructure, what really matters is the labels, right? So having your subject matter expert create a labeled data set and maintain that over time, that really becomes the bottleneck in our opinion, not having a deep learning expert on staff. So those are some myths. Hopefully that makes sense. Those are 3 things that we just believe are false about deep learning. But at the same time, there are some really real challenges. So I want to spend the bulk of the rest of our time today talking about some of those challenges. These systems are hard to deploy. It's not trivial, right? Especially in a production environment where you have to have very high uptime. So let's talk about them here. So we broadly divide the challenges into 3 areas. So the first one is deployment, the second one is maintenance, and the third one is change management, kind of at the organizational level. So we'll go through these one at a time. We'll tell you how we have solved these problems, and I think it gives you a pattern for some best practices and some suggestions about what makes this hard and what to think about as you're thinking about getting into deep learning. Or if you already have a deep learning system, maybe this can add a layer of ideas on top of that. So deployment, right? Why is deployment hard? So to be honest, everything that I've shown you so far could be completed by a student in my class at the University of North Carolina. So I teach a graduate level class. I've got some really great students. And as far as the training goes, they're all, this is not, in our opinion, the tools have gotten so good for training that I no longer think that's really a bottleneck. Now, the challenge, though, is to get that model into a production manufacturing environment. That really, we think, is a much bigger challenge, and that's where we spend a lot of our time as an organization. One reason it's hard is because you need accelerated computing. So you need generally a GPU, a graphical processing unit. This company, NVIDIA, kind of has a lock on the market right now, unfortunately, but they do make great hardware. So you need a faster computer. Another issue that we come into all the time is that many companies have significant investments in vision already. You can spend a lot of money on hardware, and generally we don't want to rip and replace this stuff just to add deep learning. There are a number of cases where we'll do new installations, and for that we'll use a systems integrator to help us with cameras. But generally, it's good to be compatible, right? And that can be difficult based on bullet point 3 there, which is that a lot of these systems today are kind of closed, right? There aren't as many open standards around vision as we wish there were. There's things like GigE, but there's not much of a protocol out there for image storing, things like that, image transfer. I think PLCs in general have done a better job at interoperability than vision systems. So those are some of the challenges we see in deployment. And let me talk you through our solution, or how we address this. So the first thing we do is we use on-premise hardware. And to some of you, that's going to be a no-brainer, right? But you talk to some cloud folks, and they may raise their eyebrow. But we think having a GPU-accelerated machine in the factory is critical. This gives us the uptime that we need, and we think it's the right move infrastructure-wise. On the compatibility side, we try to make that box as compatible as we can with existing hardware. So usually over the LAN network, we have some other options, but usually over LAN. We'll grab the images we need, either from cameras or from a full vision system. And we do all of our processing locally on that box. And we send those outputs back out either through TCP/IP or through various protocols back out to PLCs or whatever kind of integration we need. That's really the backbone of our deployments, is a GPU machine. And then this will kind of get us into the next challenge, but we also use a cloud component pretty heavily. Now, some manufacturers get nervous when you say cloud, and that totally makes sense to us, right? I mean, you can't have, these systems cannot go down, right? So we can't have cloud dependency. So we don't. Our real-time decisioning happens completely on device. We use the cloud for a few things. The first one is monitoring and reporting. So we have a centralized location where we store all of the images that we need and all the metadata. We tie that to quality analytics as well, dashboards, all that good stuff. And we also do model retraining in the cloud, and the models get pushed back down to device. We think having that infrastructure in place is a critical part of deploying deep learning systems, and we'll hash that out a little bit more in the next bullet point here. So that's deployment, and that's our approach to some of those deployment challenges. The next one is model maintenance. So I haven't heard this talked about in the quality space too much yet, and I'm really curious to hear various approaches. We have a certain approach which I'll share with you, but it's a big deal, and I don't think it's been talked about as much as it will be, I think. So the idea here with model maintenance is that model performance will degrade over time. So deep learning models and any kind of machine learning or even traditional computer vision, as soon as they're put into production and the world starts changing around them, your performance will degrade. That's called model drift often. The rate at which it will degrade is an open question, and this is what we monitor carefully at our customers' installations. In some industries, like if you zoom way out and think about like the financial industry where they've been deploying deep learning for 5 to 10 years, or you think about companies like Google that deploys deep learning models every day to help search algorithms, they are retraining very frequently. So in fintech and in financial industries, they retrain models on the order of daily, right, hourly or daily. In manufacturing, we don't think, and based on our experience, that kind of cadence is justified or wise, but we do think that, and we've observed, that things will change on your manufacturing floor. You may think that it's locked down, but things, they just change. A certain color of a part might change, a supplier might change the chemical ingredients they're using in one of your parts. And we think that being able to detect that something has changed and quickly adapt to it is a critical piece of making deep learning work in production. One more point on that, sorry, before I move on. So as I was saying, in the financial industry, retraining happens hourly, daily, things like that. We've observed that in manufacturing, you want to think about kind of the monthly to quarterly cadence for model maintenance. And we found that to be a pretty reasonable cadence to make these things work. The other challenge, and I've kind of gone into some solutions, but let me mention one more challenge here. The other challenge is knowing when your model's not doing well. So, all the accuracy numbers that I've provided you, those are based on human labels. So unless you have a human labeling all of your data, you can't track accuracy over time, right? So how do you know, right? What do you do? So let me talk about our solutions to those problems. So the first one really comes from our cloud component. So we aggregate data from multiple production lines into a centralized repository, and we use that to build dashboards like the one you're seeing on the screen. So we'll track kind of typical things that manufacturers are interested in, such as defect rates. How many defects per hour are you getting, and based on the defect type. But we also, and the thing I really want to call out here, is we track something we call either anomalies or kind of unknown predictions. And this is our main mechanism today for monitoring model health. So let me drill into that with you and talk to you how we determine if something is an anomaly, if something doesn't quite fit with the model that we've trained. So here's one last experiment that I'll show you. And again, I'm using that MVTech dataset. So what I did here was I tried to simulate what would happen if a new defect came along, right? So what if I train my model on Monday, deploy it on Tuesday, and there's some new defect on Wednesday, right? What's going to happen? So this is, again, the MVTech dataset. And I went off and I trained a ResNet 34 model again. But I excluded, intentionally, I excluded one of the classes. So I left glue out of training. So no glue showed up in the training data. So then I went on and I ran this model on this data, and this is a test set. This is not training data. And what we're looking at here, so the columns represent the true labels. So that first column, it says color way on the top. Those are all actually color defects. The second column is all cut defects. The third column is all fold defects. Now, if you look in small text right above the image itself, that is the prediction, right? So that little Y hat, that means what is the model predicting? You can see that our model gets all the color examples right. It gets all the cut examples right. It gets all the fold examples right. When we get to glue, though, right, glue is nowhere to be found, right? And that's because there was no glue in the training set, right? So glue is not a concept, right? There's no way the model will ever predict glue. So how do we handle that, right? So what we do is we use another output of our deep learning model. So the way that these models work generally, if you're using something on the output called a softmax layer, is you also get a confidence prediction. So you get the prediction, you know, color, cut, fold, but you also get a confidence level. And that's the C that you're seeing, the C equals. So that's a probability. It's between 0 and 1. And if you look at the color column, you see that the prediction is 99% confident, 99% confident, 100% confident. So generally very, very high, right? Now, if you slide to the glue column and you look at the confidence, you'll notice that it's significantly lower. In most cases, not all. But the reasoning there and what we see in practice is that the model has not seen that class before, so it's generally less confident. So in practice, we threshold this. We say if confidence is below X, then this must be what we call an unknown example, and we track that over time. So if you have a spike in unknowns, it's worth investigating generally, right? It's something to have a better look at, and it may mean it's time to retrain, maybe to add a class. So this is something we monitor over time, again, using our cloud infrastructure, and we think this is a really important piece of keeping the systems healthy and functioning well in production environments. Okay, so I'll address one more piece, and this is kind of the change management piece. So if we think way back to that early slide I showed where I was comparing traditional computer vision versus deep learning, right? I mentioned that, hey, you know, deep learning can get you dramatically better results, right? But it kind of comes at it is a cost, so it requires change. Your organization is going to have to change. And I'd say the best way to describe that change is now data, image data specifically, has to be at the center of your quality process. This is kind of part of a broader trend that we're seeing. We're seeing with all these systems like Ignition and OSI Soft Pi, and we make a system called SpyTest Connected Factory. With all these systems that are able to aggregate data, decision making in manufacturing is becoming much more data driven. And we think that incorporating image data with that decisioning is really critical to the success of deep learning deployments. So I think just to give you a tangible example here, you know, today in production, maybe you have people doing visual inspection of every part. Really where we see that going is those same resources, the same people who know how to do that, their knowledge needs to be repurposed into labeling and monitoring these systems. And the beauty is that you're actually using their intelligence way more effectively. So so they know what good and bad looks like, right? Instead of having them look at every part, have them create a labeled data set, right? And then you can automate their decision making, right? But not automate them away in that sense. What we see is that those people who have that quality knowledge, their skills are then used to monitor the system, create new labels when it's needed, and you're scaling their time, right? So instead of watching a production line for 8 hours, I can spend half an hour labeling and monitoring, and then I can use my time for other things. So that makes a huge difference, right? We think that it's best to think about deep learning as a continuous improvement technique, not as something that you're going to train one time, deploy, and be done for 10 years. So that's really the change management piece. And this really is important. If you're working on deep learning as part of a company and you're trying to sell this internally, that's also an important thing to keep in mind, is that it will take some changes on the organizational front. Okay, so I just have a few wrap-up slides here, but I'll just briefly kind of cover what we discussed here. So we talked about a few myths that we think are just false, and then we discussed a few challenges in deep learning, deployment, model maintenance, and change management. So we're happy to answer questions on those. I see we're already getting some questions, which is great. I will just share 2 or 3 more summary slides about some results we've seen and a little bit about Mariner, and then we will open it up to questions. So I'll share one more broad results slide with you, and this is generally this kind of frames how we start these deployments. So here's some results we've been able to achieve through deep learning. These are real numbers from customer deployments. And if you're in a position where you think deep learning could be a good fit for your organization, we really encourage you to start with the business case, right? So this is the case we make to our customers, but also internally, if you're trying to convince management that this is a good idea, then these are the kinds of arguments that we find resonate well. So just looking at some results here, so when you have this precise, rapid, and adaptable visual inspection, like deep learning, it can drive all kinds of value for your business. So we already talked about reducing false rejects. We talked about improvements over manual inspection. But there are a number of other areas that we were pleasantly surprised by when we started getting these systems into production. One area that's really interesting is root cause analysis. So as I mentioned, if you're able to tease apart 15, 20 different defect classes and tie that to real-time reporting and alerting and monitoring, as we do, all of a sudden, you can optimize your overall production way more quickly. So we had a customer who their reporting cadence was, I think, around monthly. So every month they would say, okay, how many of this kind of defect did I have? Let me go investigate my production. They can do that now in an order of minutes. So being able to do root cause analysis and other things that we're mentioning here, it can really make a huge impact for the business. So as you're thinking about how deep learning fits in, I encourage you to think maybe just a little more broadly than just improving output quality. Improving output quality is certainly a wonderful goal, but there's other benefits to implementing a system like this. And then finally, just a little bit about Mariner. So we are a full-service manufacturing analytics shop. So we offer a range of consulting services, and then we also have 2 products in the marketplace. We are Microsoft Azure Gold partners, so we build our infrastructure on Microsoft Azure. Our 2 products are Spyglass Connected Factory, which is a connected factory telemetry solution, and we also offer Spyglass Visual Inspection, which is what you heard about today. And then finally, I'll just share a little bit about how we start these things. This is how we start a project, and I think it's also just this is how we recommend anyone start a project. So first, it really starts with that business value. Why are you doing this? Is it going to save this money? Is it going to improve that output quality? What are you trying to do? After you've defined success, we find it's very helpful to then move to images. So get a sample image data set. It doesn't have to be thousands, tens or hundreds is fine. And then we train a model, right? We say, okay, what kind of performance can we get from deep learning? And will that deliver the business goals that we need? So that's how we typically do deployments. And then we basically the first part of this has a money-back guarantee. So you can try these first 2 steps with us, and if we can achieve your goal, we move forward. If not, we stop. So that's how we do that today. And then I'll go ahead and stop there. Let me just say, if you'd like to learn more about our solution, please visit mariner-usa.com. And we love hearing about detailed applications. So if you have a deep learning application or just have some questions, feel free to email me directly. My email is steven.welch@mariner-usa.com. So thanks for your time today, and I will turn it back over to Dennis.
Thank you very much, Stephen. We will now begin our Q&A. Just a reminder, if you would like to ask a question, please use the Ask a Question area to do so. And with that, let's go to our first question. When is it better to use color versus monochrome images?
Yeah, great question. So we have some customers who use monochrome. Mostly it's to save space, as far as we know. The thing is, you can always convert a color into monochrome. Now, there are some hardware advantages of a monochrome camera. So sometimes if you go monochrome for your hardware, you can actually get higher resolution, things like that. We generally prefer color, though, just because color gives you more options, right? You can always make it black and white in software. So unless you need really high resolution or you're struggling with data rates, then we really recommend color. We generally train our models on color images first. We may try black and white if we need to, but color is definitely our first choice, and then if there's a good reason, we'll try black and white.
Next question also has to deal with color. Let's say we have a product that comes in multiple colors. Does the system require a picture of each color, or can the system pick up defects regardless of the color?
Yeah, that's a great question. So I wanted to show an example of this today, but I didn't quite have time in the hour time slot, unfortunately. But it's a really interesting question, right? And it speaks more broadly to how generalizable is a model, right? If I have 10 different kinds of products or 100 different kinds of products, do I have to have a different model for every product, right? And we've generally found that the answer is no, but there are some restrictions around that. So another customer that we've deployed with is a discrete part manufacturer, and they have around, I think, 50 to 100 different parts. For them, we were able to deploy one model, and their parts do have different colors. And we were able to deploy one model, but there is a little bit of a catch. So the catch is that whatever you're looking for needs to be relatively consistent across your products. So if your red product has a certain kind of scratch on it and your blue product has a certain kind of scratch on it, as long as those both are the same kind of scratch or they look visually similar enough, then you can generally train a single model that will capture those both well without having examples of all the colors. So with that customer that had 50 to 100 SKUs, we trained off around 5 to 10 of those, and that generalized across the rest of the SKUs fine. There are limitations, and I'll just mention one more technique that helps with this. There's this idea called data augmentation. We have another customer who has a really broad range of colors, and we use what's called color space augmentation. So when we train our model, we synthetically perturb the color of the training images to simulate if the part had been a different color, and that helps it generalize as well. So there's lots of options out there. Generally, you don't have to have examples of all your colors, but there are a few caveats to be aware of.
Next question, how would you utilize classification if you have, for example, an inspection where defect location and type and cause are equally important?
Wow, okay, great. So the question was, how would we use classification if, and make sure I get this right, Dennis, that's a good question. So how would we use classification if the defect type, location, and cause are equally important? Did I get that right?
Yes, that's correct.
Okay, cool, thanks, awesome. Yeah, it's a good question. So that might not, actually, I would rule out classification for that use case. If you have to have location, and I'll just go ahead and slide back to that slide really fast. I think I can pull it up quickly. If you have to have, there it is. If you have to have location, then you need to use detection or segmentation. As far as the cause versus the type, we generally try to roll that into one thing. So if the cause changes the appearance, then we can detect that, right? But if you have some cause, like multiple causes of the same defect, but they don't change the appearance, then we can't get that. So generally, we lump cause and type into one thing that we just call type, and maybe you have 2 different versions of the same type for different causes, and as long as they look different enough, we can capture that. But if location is what you need, then we recommend detection or segmentation. Good question.
Next question's more general. How do you characterize if a problem is suitable for a deep learning solution in the first place?
Yeah, great question. So I encourage you to explore traditional computer vision first, especially if you have a simple problem like presence absence detection, things like that. There are versions of presence absence where they get harder and deep learning can really help. But I encourage you to look at kind of the off-the-shelf simple computer vision problems or approaches first. Now, in many problems, and especially in new areas, deep learning can really be a good solution, and we think that's going to grow into more and more areas. And generally, the litmus test that we like to use is this. So if after you take the image, after you have your image formation step and you have an image, if a human can tell the difference, if a human can see what you're looking for, right? If a human can say, oh, that part has a scratch, this part has a this, then generally deep learning can do it as well. There are some limitations, but if a human can see it in the image, then we generally think that's a candidate for deep learning. And now, as I mentioned, because the infrastructure is developing, so because deep learning is more complex to deploy in some cases, then also look at traditional approaches, I would say. But if a human can see it in an image and it has real business value behind it, then we generally think it's a great fit for deep learning.
Next question, speaking of traditional machine vision. In traditional machine vision, there's a lot of focus on lighting and optics to make sure we capture the best contrast between defects or features of interest and background features. Is this focus on lighting and optics just as important in deep learning applications?
Yeah, so that is man. I would we have some theories and some early results on that question, but I'm very curious to learn the full answer to that question. It's a really great question. So yeah, traditionally, the lighting is probably more important than anything else, I'd say, from what we've learned and what we know about the industry. And I certainly would say, based on my experience, that the lighting and camera and hardware configuration, they matter less when you're using deep learning. The question is how much less, right? Can I go replace every vision system with a cell phone? No, definitely not. The formation still matters a lot. But I think a really interesting question is, how much less do they matter, right? How much less time and effort can you spend on your physical setup if you're using deep learning? It's definitely, I think, a balance thing, right? Where there's got to be a balance between the two, the software and the hardware. But we do think that the presence of deep learning moves the balance towards the software side, where the hardware does matter less than it used to.
Next question, is there a way to group unknowns based on a common pattern that can be used to label them later?
Yeah, that's a really good question. So you've hit on this big area, you probably already know it, this big area called unsupervised learning. So in unsupervised learning, the idea is that I'm just going to give you a bunch of images, and we're going to try to automatically kind of cluster those images based on similar visual patterns. So if you're interested in unsupervised learning, definitely send me an email. I can send you some papers to check out. Unsupervised learning is generally less mature than supervised learning. That's generally why we use supervised first. But there is a tremendous amount of research out there. To us, none of it appears quite production grade yet, in our opinion. But there's a huge body of literature, and if you shoot me an email, I will send you some cool papers to check out.
Next question, does training on non-inspection data sets like ImageNet that has many millions of images impact performance of a deep learning system?
Yeah, dramatically, right? Yeah. So, actually, no, let me make sure I understand your question. So the answer is yes, but because your question, and this is a question I had early on when I started working on visual inspection. So before my job here, I worked in autonomous driving, designing deep learning vision systems for autonomous cars. And I had the same concern, because when you look at, especially some of like the monochrome and some of the very carefully lit images in manufacturing, they look dramatically different than a data set like ImageNet. ImageNet's just like a bunch of images you take on your cell phone, right? So it seems like the worlds are kind of different, right? Like wouldn't we prefer to pre-train on something that looks closer to the data that we're going to deploy on? And this is kind of one of the mysteries of deep learning. So, when I first started at Mariner, I actually did not use transfer learning because I thought the same thing. I thought, the ImageNet's too different, right? It won't generalize. We can't transfer learn. So I did that for a few months, and then some new papers came out, and I did some thinking, and I did some experiments. And even though ImageNet looks different, you are dramatically better off training from it. Now, if there was some magic manufacturing data set that had 1 million images from manufacturing applications, that could be better, right? Now, the chances of that showing up anytime soon are pretty much zero, I think. But in practice, we found that you're much better off with any kind of image data set, even if it looks different than the data set you deploy on. That's kind of one of the really fascinating things about deep learning, is how general it is. It can learn from ImageNet, and you can deploy it and fine-tune it on very specialized images from manufacturing.
Next question, are 3D images and point clouds easily included in training models?
Yeah, good question. So 3D images more so. So the challenge is this. So we didn't have time to talk about the actual architecture. So all the models I showed you today are what are called convolutional neural networks. And they assume that you have a spatially uniform input grid of data, right? So like a grid of pixels, right? Now, if you have a 3D image that still adheres to that structure, so I'm thinking of like a CT scan in the medical industry, for example, or other kinds of 3D images that are sampled on a uniform grid, then yes, we can definitely train a convolutional neural network. There's some papers that get great results. Point cloud is harder because you no longer have that spatial uniformity. So you can't use the convolutional operation as cleanly. There is some work on this, and in autonomous driving, there's a sensor called LiDAR that has the same problem. So we have not done anything on point cloud. I think it's interesting, and there's definitely some work out there on it, but I don't think it's as easy of an application as a 2D or a 3D image that has that spatial uniform sampling.
Next question, do parts or products have to be stationary to view, or can this work on a line that is moving?
Yeah, good question. So I went a little bit fast, but the application that I shared at the beginning of the hour, that is on fabric that's moving at a rate of 85 yards a minute, so it's flying. The only challenge is that you need to have a camera that has a fast enough shutter speed to not incur motion blur. So as long as your hardware is set up in a way that you won't get motion blur from a moving part, then this will work exactly the same way as it would on a stationary product.
Next question. Can you provide some examples of the types of hardware you use and how it is connected to the cloud? For instance, if the customer already has an on-premise data center with GPU-accelerated hardware, could you deploy your application on that? And how would you handle this for customers that do not have internet connectivity?
Yeah, great question. So those are kind of two ends of the spectrum, right? So if you have an on-premise data center with GPUs, then yeah, our preference is going to be to deploy on your existing infrastructure. So really, at the end of the day, we're a software company. So we are very much able to do that. We do have one restriction today, which is it has to be running Linux, but that's more and more common. So that's how we would handle that. We would install on the existing hardware wherever possible. And then two, if someone has no internet, right? So this is a discussion we've had internally. We haven't had to do one of these yet. People generally come around to using some kind of basic cloud infrastructure. But if you don't have the cloud, we can still certainly deploy this. I think there's two reasons you might not have internet. If you're kind of in the camp where it's just not an important part of your manufacturing process, or you're in a remote location, or you just don't have it because you don't need it, that's a little bit tougher because some folks have the concern where they don't have internet for privacy issues. If that's your issue, then we can actually deploy the full stack on premise. So we're Microsoft partners. They have a product called Azure Stack Edge where they deploy essentially Azure servers on premise. So we can totally do that. But if you're in the camp that you just don't want any of this kind of IT infrastructure laying around, that's a bit harder. We can still do it, but I think we would think carefully about how we would handle the retraining. Pieces like that would be more complex. So it's doable, but not our preference, and it does slow things down, I would say.
We are over the 1 o'clock hour, but Stephen has graciously agreed to answer a few more questions, so we'll answer a few more. The example applications you gave us, fabric, leather, or screws, those are all products that are supposed to look the same. Can you point to examples of successful deployment of a deep learning system where the samples are non-uniform, but human observers can still detect defects?
Right. Really interesting. Yeah. If you would like to follow up on this question, I'd love to hear more about the exact application that you're thinking of here. So I think, if I understand the question correctly, I think we're talking about the thing to look out here for. So there are certainly places where deep learning is not going to be the right fit, right? And the trick here that we've observed, or the thing to pay attention to, is whatever you're looking for deep learning to pick up on, right? You may have wildly different looking products, right? But is the thing that you're trying to detect, either a scratch or a defect or whatever it is, does that have a common appearance? It doesn't have to be exactly common, but relatively common appearance across those very different looking non-uniform parts. If it does, we found that in practice, generally that works pretty well. And a single deep learning model can still generalize even if the part itself looks very different, as long as the thing that you're looking for, the defect or whatever, is consistent. Now, you may be thinking of something different, and I'd love to hear a little bit more. So if you want to shoot me an email, I'd love to discuss more. But that's the way we've encountered that type of problem in the past. And like I said, as long as what you're looking for is consistent enough across your different looking parts, we've been able to get good performance.
Next question. We understand that GPUs are excellent for training deep learning networks. Do we need to use GPUs for scoring as well?
Yeah, good question. So the webinar last week, I think Dr. Lau is his name. I think he did a great job talking about the different embedded systems. So we deploy on GPUs today. Mostly that's so we can achieve the inference times that we need. So you can deploy this on a CPU as well. Just to give you a rough example here, so we have a customer who has very large images of parts. So the images are on the order of 100 megabytes. They're 10,000 by 10,000 pixels. For that customer, we deploy on a NVIDIA GTX 2080 GPU, so about $1,000 GPU. We can do inference in about 10 milliseconds, and they need a decision in about 2 seconds for their production line. So that's within spec. If we had used a CPU instead, we would have been around 10 seconds, so it wouldn't have worked. So you can definitely deploy this on a CPU, or you can deploy it on the various accelerators out there. Intel makes an accelerator. I will say that a thing to keep in mind is that NVIDIA has done just a great job at building a really robust tool chain called CUDA. So deploying on GPUs is really easy, right? So if it's an option, I encourage it, but you certainly don't have to have it. You can deploy on CPU. CPU will be on the order of 10 to 1,000 times slower, depending on what you're doing. And you can deploy using other accelerators as well.
Next question, could deep learning systems use multi-spectral images?
Yes, there's several really good papers on this. If you want to read the paper, send me an email. So yes, it's really cool. So RGB images are just 3 color channels, and multi-spectral can have many more color channels. I know some cameras have 16 color channels. It's really cool to think about. We can't see in that way, but cameras can. And yes, there's some really great papers. I think there was actually one, I think it was in Vision System Design, talking about using hyperspectral for an agricultural application, I think. But there's some papers I can definitely send you, and the approach is very similar for hyperspectral.
So would that imply that you can also train on infrared images?
Yes, yeah, absolutely, yes.
Okay, we have a lot of questions. We have time for just a few more. Let's see. Does deep learning apply to metrology inspection?
Yeah, so for those of you who don't know, and I believe this is the sense that the user is using it in, so metrology is when we're trying to do it. It's very similar to the idea of gauging. So we're trying to measure the size of a part. Is that fair, Dennis, based on your understanding?
I'm sorry. Could you say that again, please, Stephen?
So metrology, to me, that means we're trying to measure or gauge the size of a part.
I'm not actually sure, to be honest with you. I would have to go.
Oh, no worries. Okay.
I would have to go onto the website to see.
No problem. So I think that's what our audience member means. I'll answer it from that perspective. So yeah, it's a little bit different, right? Because we talked about classification, for example, which we're trying to, get a discrete class out of a model. With metrology, like maybe we're trying to measure, okay, this screw is exactly 1.35 inches long or something, right? So you can do that with deep learning. So back when I worked in autonomous driving, we trained a bunch of models it's called a regression model. And what that model did was it actually predicted lane markers or detected lane markers, and then we can measure how big the lane is, right? So you can certainly do it with deep learning. Sometimes it's overkill. A lot of the existing traditional computer vision approaches to metrology are good. And we haven't run into a case yet where it made sense to solve a metrology problem with deep learning. It's generally been kind of overkill, but you certainly could. We have one customer we're talking to that we may try it on. The technology is there. It's called a regression problem, and you set up the model a little bit differently, but the same idea applies. But I would say that if you're looking at metrology, make sure that traditional computer vision won't solve it first. But it definitely is achievable.
Okay, we're going to make this our last question. Can you please explain again how you were using deep learning models for root cause analysis? Or in other words, are you able to tell which inputs cause the defect?
Yeah, great question. So let me talk through it here. So this is in the context of one of our customers here, and they now have like 20 different defect classes. But let me explain. So this is the fabric example. So if let me pick a different kind of example. So there's a different kind of fabric defect called a pick. That's when you have a little bit of, think about it as yarn coming out of the fabric. So using deep learning, instead of just detecting, hey, this fabric's good or bad, we can say, okay, it's bad, and the cause, because one of these defect classes might be pick, so defect 5 might be pick. We can say, okay, on this roll, we saw a lot of picks, right? So what that does then is that's tied up to their MES system. So their manufacturing execution system knows that roll came from this machine up in the line that could have caused those picks. So if we see a high volume of picks on a certain roll, using our integration to their MES system, we can flag that and say, okay, this machine needs to be adjusted. So that's what we mean by root cause analysis. So by having all these different defect categories, we're kind of assuming that a category is associated with a cause, which for some applications it is, for some it's not. In this case, it really is. So if they see a stain, they know, oh, this had to be caused by this, or it at least narrows it down pretty significantly. So by having all those granular different kinds of defects, and I guess I could even show the leather example, right? So if you saw a bunch of glue on your leather, right, that probably came from a different place upstream in production than the cuts, right? So that I can say, okay, I need to go look at this certain machine. So that's what we mean by root cause analysis.
With that, on behalf of Vision Systems Design, I would like to thank Stephen Welch and all of you for joining us today. If your question was not answered, we will be forwarding these questions to Stephen, and he can get back to you directly. This presentation will be archived within 24 hours and can be accessed from the homepage at visionsystems.com. The slides will also be available for download today. A reminder email message for the archive will be sent to registrants, complete with a direct link to the archive. If you have any questions about today's presentation, please feel free to email me at dsemeka@endeavorb2b.com. We thank you again for joining us today and look forward to providing you with webcasts in the future.